Hi everybody, it's Dr. Schultz here. Welcome to this video lesson on force addition in 2 dimensions. We've just spent the last several weeks getting really familiar with Newton's 3 laws, and I think it's safe to say that you're all experts in the 3 laws at this point. What we're going to do next is get a little more sophisticated, and we're going to be looking at how forces add in 2 dimensions and looking at what types of accelerations can be produced in those situations. So the goals that we're going to cover in this lesson are goal 4.5, which is to determine the net force acting on an object when one or more forces act on it in 2 dimensions. And specifically, we're going to be looking at target B, which is to use the component method to determine the magnitude and direction of a net force acting on an object in 2D. Before we get started with this, I just want to remind you to make sure that you're taking notes, and there are going to be some problems that you can solve along the way that you should definitely solve on your worksheet. And please feel free to pause the video whenever you'd like so that you can take some time to think about what's being presented and how you're going to solve the problems. Okay, so let's go. We're going to start off with the statement of Newton's second law, which states that the acceleration of an object is proportional to the net force that acts on it, and it's inversely proportional to the mass. This is oftentimes rearranged and written as the sum of the forces on the left-hand side are equal to the object's mass times its acceleration on the right-hand side. And in class we've talked about how writing Newton's second law this way is really kind of looking at it in terms of cause and effect, where the sum of the forces on the left side is the cause of the change in motion, and the acceleration is actually the effect. Now, the type of problem we're going to look at in this lesson is a problem in which the forces are not along a line. So I have a picture here that shows 3 different forces acting on a mass. You can think of this as a hockey puck. And the goal is to determine the net force and the acceleration of the mass that results from these 3 forces. So one way of determining this is to recognize that forces are vectors, and you can use a graphical method for adding those vectors. And we've done this already in class with velocity vectors. The graphical method that we've used for adding vectors so far has been called the head-to-tail method. So you can imagine if you have 2 forces, F1 and F2, and you're asked to add them by the head-to-tail method, what you would do would be to connect the vectors in a head-to-tail sort of a way, like we've done before. And the net force would be the resultant vector. And that's the vector that goes from the beginning of F1 to the ending of F2, or from the head of F1 to the tail of F2. And that net force is itself a vector answer. It's a vector sum. Its length has a meaning and its direction has a meaning. If we were to think of putting numbers into this problem, make F1 equal to 40 newtons and F2 equal to 30 newtons. Okay, we can see that the net force is going to look something like that, and hopefully you're thinking along the lines of that net force having a magnitude of 50 newtons. Yes, that's a 3, 4, 5 triangle, and if you really would like to do it with the Pythagorean theorem, you can of course Pythag 40 newtons with 30 newtons to find that 50 newtons, or you can just recognize that it's a 3, 4, 5 triangle. To find the angle that the net force vector makes with respect to the x-axis, you can take the inverse tangent of the opposite side over the adjacent side of the triangle. So 30 divided by 40, and that's about a 36.9 degree angle. So that's useful to know, and you could take it one step further. You could actually find the size and the direction of the acceleration of a mass if you were told that the mass is, say, 5 kilograms. Okay, and that's pretty easily found by taking your net force of 50 newtons and dividing by 5 kilograms. And so you would know that there's an acceleration of 10 meters per second squared that's caused by this net force. And it's very important to say that the direction of this acceleration is exactly the same as the direction of the net force. And that will always be the case for Newton's second law. So to kind of summarize here, what we did is we used the head-to-tail method of vector addition to add two vectors in a very simple way. We found their net force, and then we used the net force to find the acceleration of the object and determine both its size and its direction. And this is the primary utility of Newton's second law, is that you want to figure out what's the net force on an object and what type of acceleration does it provide. Now, what we're going to do next is we're going to look at cases that are slightly more complicated. And oftentimes the head-to-tail method is too cumbersome to actually draw out. And what you'd like to do is to use some sort of an algebraical method of adding the vectors. And we've done this before with velocity vectors, and now for the first time we're going to do it with force vectors. And this is called the component method. And the idea is that you can take Newton's second law, which is written here in the middle, okay, F net equals ma, and the idea is that that law applies separately to both the x direction and to the y direction. And so forces can actually be resolved into x and y components, and the components can be added up separately. And you can determine the accelerations in the x and the y directions separately. And everything works out nicely. So let's come back to the example that I had presented just a few minutes ago. And let's say that you want to add the vectors of 40 newtons plus 30 newtons, where 40 goes to the right and 30 goes up. To do this by the component method, you need to make a table. And the table should have an x column and a y column. And I usually like to put a column in the front that lists the forces as they're labeled. And what I would do is I would just break down each force in terms of its x and y pieces. So F1 has a component in the x direction of plus 40 newtons, and it has 0 newtons in the y direction. And similarly, F2 would be 0 newtons in the x direction and 30 newtons in the y direction. And so we have examples here of vectors which are horizontal and vertical. What you do next is you add up all the numbers in the x column, so 40 plus 0 equals 40, and you add up the numbers in the y column to get 30, and these two numbers in the bottom row are the components of the net force vector. And what I like to usually do is make a new sketch and make the sketch show an x component of 40 newtons and a y component of 30 newtons, and let those two components guide the net force that I end up drawing, which is of course the diagonal to that figure. Now this is actually, it might seem like a little bit more work than the head-to-tail method, but when you have a list of forces of 3 or 4 or 5 more, this is the way to go. Because it's very easy to add up columns of numbers rather than drawing really fancy pictures. Okay, and I just put a note here on the side that, what happens if, if your components of the net force don't happen to be like a 3, 4, 5 sides of a triangle. What if it wasn't 30 and 40? Well, hopefully you remember that you can always Pythag the components to find the exact size. And you can always use the inverse tangent function to find the angle. So that's useful, of course, whenever your net force is part of a triangle that's not a special triangle. The other thing that we can find out and learn from this method is you can actually go the step further, and you can learn about the acceleration of the object in both the vertical and the horizontal directions. And this is kind of new to us, and it's kind of neat. You can actually write Newton's second law, acceleration equals net force divided by mass. You can write it in the y direction. And in this example, we could take our 30 newtons of vertical force and divide it by 5 kilograms. And we find out that in the y direction, in other words, vertically, the object accelerates at 6 meters per second squared. You can do the same thing in the x direction, and you just have to be sure to use the x component of the net force of 40 newtons. And it turns out that in the x direction, the object accelerates a little bit more at 8 meters per second squared. Okay? So the idea here is that acceleration itself is a vector, as we've talked about in this class, and it has components too. And you can find the components very easily if you know the components of the net force. to wrap this up, maybe you're expecting this, but you can combine these two components, and by simply Pythagoreaning them, you can find out the magnitude of the object's overall acceleration. So in this problem, let's say that it's a hockey puck that we're pushing on. The hockey puck is going to accelerate in kind of a diagonal way, and its acceleration is going to be the combination of 6 meters per second squared and 8 meters per second squared. The vector combination, I should say. So when you combine those two accelerations as vectors and you Pythag them, you find out that you get an overall acceleration of about 10 meters per second squared. This is good because it happens to also agree with the acceleration that you would get by taking the net force of 50 newtons that we figured out in the last slide and dividing that by 5 kilograms. That also turns out to be 10 meters per second squared, and that's not a coincidence. So there are different ways to find the overall acceleration. You can find it by components, or if you'd like, you can find it by simply taking the net force and dividing by 5 kilograms. In certain types of problems, you want the components. For example, in projectile motion, we were very interested in using components only. But sometimes you want to use the overall acceleration, and it's just easier to use the net force divided by mass. So, kind of a strategy for using the component method is, first of all, to draw a free body diagram for the object of interest. Second of all, tabulate the x and y components of all of the forces in some sort of a table. Third, you want to sum the components in each column to find the components of the net force. If the object is known to be in equilibrium, we'll fill in zeros for the final components, and that's probably something that we'll do in class. Fourth, calculate the magnitude and direction of the net force using the Pythagorean theorem and the inverse tangent. And finally, calculate the magnitude and direction of the object's acceleration using Newton's second law. So the remaining parts of this lesson are going to consist of some examples. And I'm going to lead you through the first one, and then I'm going to ask you to do the others on your own, and I'll allow you to check your answers for some of them. So here's a more complicated example. We have 4 forces that act on a 30 kilogram object, and you must find the net force on the object and find the object's resulting acceleration. So the first thing you do is you want to take a look at your free body diagram, and in this case it's already given to you. The next thing you do is draw a table, okay? And the table should have entries for 4 separate forces, and it should have a row for the net force. So in this problem we have 2 horizontal forces and 2 vertical forces. That's going to mean we're going to have some easy zeros that show up in the table. And I'll give you a second to have a look at some of these components. So horizontal forces, like force number 1, have a 0 in the y column. Vertical forces, such as number 2, have a 0 in the x column. And so that's not too bad. You take your values in the x column, you add them up, they add up to 100. In the y column, they also happen to add up to 100. We now know the components of our net force. I think it's a good idea to make a sketch someplace else in which you start with those components of 100 newtons right and 100 newtons up, and then you can find the vector, the resultant of those 2 components. Okay, this happens to be a special triangle, doesn't it? It's a 45, 45, 90 triangle. And so the net force here happens to be 141 newtons. Okay, so by the Pythagorean theorem you can determine 141. By an inverse tangent you can get 45 degrees, or you can just recognize the triangle. If you work out the acceleration of this object, you have to use the fact that it's 30 kilograms, and you can find the x acceleration and the y acceleration separately. Of course the sizes are the same here, but their directions are different. You can also figure out the overall acceleration by dividing the net force by the mass. If you notice, Pythagorean 3.3 with 3.3 will actually give you 4.7. And so the accelerations also can be combined by the Pythagorean theorem to find the net acceleration. Okay. Example 2, I'm going to ask you to read this and complete the table, and then go ahead and find the net force on the object and its resulting acceleration. So at this point, I would recommend that you pause the video and work this problem out for yourself on the piece of paper that's provided. And when you're done and you have your answers, continue the video and you can check your work. Okay, so I'll hear back from you in a few moments. Okay, so I'm glad you came back. Let's see how you did. There's our force table. Okay, so negative 400 and plus 150. That's our net force diagram. So 427 newtons at 20 degrees above the negative x-axis. And I'll just state the final accelerations here so you can check your work. So hopefully you did okay with that, and I hope that you drew this secondary diagram. I hope that you drew a nice table, and I hope you showed your work for the calculations. Let's do a third example, and in this third example you have 4 forces acting on an 8 kilogram object. And I'd like you again to do the same thing, find the net force on the object and its resulting acceleration. The difference in this problem is that you have a force that's a diagonal force. It's the F3. And the way that I would like you to handle this is to use the fact that there is a special triangle that's built into that vector. Okay, there's a 30, 60, 90 triangle. And to kind of remind you of the proportions in a 30, 60, 90 triangle, I've shown them below the figure. So please complete the table without using trigonometry, but simply by using the ratios of that special triangle to help you with force number 3. Okay? So I'm going to let you pause the video, do your work, and then come back in a couple minutes and check out your answers. Okay, and here we go. Your table should have values that look something like this. Pay especially careful attention to force number 3. It's 86.6 newtons in the positive x direction, and it's 50 newtons in the upwards direction. Okay, that's how you can get, that was what you got from the special triangles. When you look at the net force, it should come out to 111 newtons. Okay, and it looks like I forgot to include the angle in the picture. There it is, 78.8 degrees above the x-axis. And you've got your acceleration components and the overall acceleration also shown on the screen. So hopefully you did okay with that. Okay, final example, example 4. In this case you have 4 forces acting on an object. The object has a mass of 2 kilograms. Find the net force and find its acceleration. This problem is a little more challenging because you have not 1 but 2 special triangles that are going to be needed to find the components of those diagonal forces. So please try to solve those using special triangles rather than using trig. And what we're going to do with this is I'd like you to complete this example on your own. And when you come to class on Monday, I'd like to check in with you and see what your answers are on this. And I'm going to use this to see how well you're understanding what's going on. So by all means, go ahead, complete this example, check your work, and I'm going to check in with you first thing on Monday and see how you're doing with the lesson. Okay? So thanks for working, and we'll see you in class in a few days. Bye-bye.